Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this subject today, I want to discuss about introduction to springs. So in this topic, we will discuss about types of springs and what are the uses of springs, and then how to calculate the torsional shear stress and the deflection of springs whenever subjected to loads. So the outcome of this topic is the student should be able to analyze the theory of pure torsion, bending to draw, shear stress distribution diagrams in circular shafts, and bending moment distribution diagrams in various cross sections. Cross sections of beams for different loading types. So under different loading types, so how to distribute the shear stress and how to draw the shear stress diagram, we will learn. So that after completion of this topic, the student should be able to analyze and answer. They can perform all these things. So that before going to the topic, you should know about the outcome of this topic. So today's the topic is springs. You know, the springs are the elastic bodies which absorb energy due to resilience. The absorbed energy may be released as and when required. So that the material having the elasticity property and plasticity property, these two properties already already in the materials topic already we have studied. So whenever the material having the elasticity property means whenever remove the load, it regain its original shape, which absorb energy due to resilience. So that energy released as and when required. Whenever required, the absorbed energy again regain its an original energy. So that the springs are said to be elastic bodies. Whereas in plasticity case, do not regain its original shape, or whatever absorbed energy, it is a permanent setup, not released as whenever required you can't. A spring which is capable of absorbing the greatest amount of energy for the given stress without getting permanently distorted. So distorted is known as the best spring, which is capable of absorbing the greatest amount of energy for the given stress. The two important types of springs are there. One is laminated leaf spring, another one is helical spring. See, laminated or leaf spring, the another name is leaf spring. So the laminated springs are used to absorb shocks in railway wagons, coaches, and road vehicles. Used to absorb shocks in railway wagons. Whenever the railway wagon undergone shock loads, these laminated springs are absorbed the energy. And similarly in road vehicles also, lorries use this type of laminated springs to absorb the shocks. In this figure, in figure 1, the laminated spring is shown. It shows a laminated spring which consists of a number of parallel strips of a metal having different lengths and the same width placed one over the other. See, this is one plate and second and third, this is master plate. Master plate or master leaf. See, in this, these two under fixed and the length of the laminated plate is L and the width is same. The width of the plate is same. So, different the lengthed metal strips are laminated one over the other. So that these type of springs are called as laminated springs. So whenever these type of laminated springs subjected to load, so then it will deflect. So that is here shown, the deflection is delta. So how much deflected? Whenever these springs are subjected to loads, you should calculate that deflection. And the design part, the how to design all these plates and dimensions, you will see, you will study in the design of machine element subject. But in this, how to calculate, what are the stresses induced in the springs, you need to evaluate. See, another one, second type is closed coiled springs. So laminated spring and helical springs. Helical springs are nothing but closed coiled helical springs. Two types again, a closed coil and open coil. So the closed coil helical springs are subjected to axial loads. So what is the definition? A spring may be defined as an elastic member whose primary function is to deflect or distort under the action of applied load. It recovers its original shape whenever the load is released. So already we have discussed in the spring definition. Elastic member property is to deflect the action of under applied load. It recovers its original shape, regains its original shape whenever load is released. Or the springs are energy absorbing units whose function is to store energy and to restore it slowly or rapidly depending on the particular application. So that you can say the springs are energy absorbing units. So in this function is to store energy and restore it slowly or rapidly. So the important types for springs are, there are various types of springs, such as one is helical spring. They are made of wire coiled into a helical form as shown in a figure. So the load being applied along the axis of the helix. So helix angle. So this like this in helical formation. In this type of springs, the major stresses in is torsional shear stress due to twisting. They are both used in tension and compression. Used in both tension and compression. This one is called wire and this entire thing is coil. This wire, the wire wound like a helical formation helix, the coil, wire coil into in the form of helical form. This is wire diameter, and then the coil diameter is capital D. So these type of springs are whenever subjected to loads, the major stresses is torsional shear stress. So how to calculate this torsional shear stress? We will see in this topic. Next, second type is spiral springs. They are made of flat strip of metal wound in the form of spiral and loaded in torsion. They are made of flat strip of metal wound in the form of spiral and loaded in torsion. In this, the major stresses are tensile and compression due to bending. See, sorry, this is spiral spring. So flat strip made of the wound in the form of spiral. Next, what are the uses of springs? First one is to apply forces and to control motions as in brakes and clutches. So in brakes, in automobile sector, the springs are used to control the motion and also clutch to regulate the speed, to apply the brakes. So to measure forces as in spring balance. This is common usage. To store energy as in clock springs. So the energy stored in clock springs. So whenever you want to utilize this stored energy, you can regain due to the elasticity property. To reduce the effect of shock or impact loading as in carriage springs. To reduce the effect of shock or impact loading as in carriage springs. So to change the vibrating characteristics of a member, as inflexible mounting of motors. So the uses of springs are in vibrating body to control the amplitude, and in automobile vehicles you can use as a dampers. So all these are main uses of springs. Now we will see the derivation part of the formulas. So the derivation of the formula, in order to derive a necessary formula which governs the behavior of springs. Consider a closed coil spring subjected to an axial load W. So this is a closed coiled spring. One end is fixed, other end is free. So whenever this closed coiled spring subjected to load, that is W. So already I told you this is coil diameter. and this small d is wire dia. See, let W is axial load, capital D mean coil diameter, and small d diameter of spring wire, and N is number of active coils. The number of active coils. So 1, 2, 3, 4, like this, 5. So these all are active coils. So whenever the spring is subjected to axial load, these coils are inactive. So it means it carry the load to top to bottom end. The C is spring index. That is how to calculate the spring index? Capital D by small d for circular wires. Capital D is mean dia by wire dia, mean coil dia. So G, already know modulus of rigidity, GRC. Length is L is length of the spring wire, and small x is deflection of springs, and theta is the angle of twist. Now, when the spring is being subjected to an axial load, to the wire or the spring gets be twisted like a shaft. See, in this diagram shown, the spring, whenever subjected to axial load, the wire of the spring get twisted like this. So like a shaft. So the theta is the total angle of the twist along the wire, and x is the deflection, how much deflected. Spring under the action of load W and along the axis of the coil. So that the deflection x is equal to d by 2 multiplied with theta. Angle of twist theta multiplied with d by 2. So distance and then angle. So again, the L is equal to pi dn. What is the length? Total length of the wire. So you can say 1/2 turn of a closed coiled helical spring. So pi d n. So it is perimeter of the circular wire. So 2 pi r or otherwise pi d into n is number of active coils. Total how many coils are there in helical spring. So you should multiply. You will get the length of the spring. So need to make some assumptions. The bending and shear effects may be neglected. For the purpose of derivation of formula, the helix angle is considered to be small, that it may be neglected. So the bending and shear effects so may be neglected. For the purpose of derivation of formula, you need to neglect the helix angle. Why? Because it is a very small angle. See, any one coil of such a spring will be assumed to lie in a plane which is nearly perpendicular to the axis of the spring. So this requires that adjoining coils be close together. With this limitation, a section taken perpendicular to the axis of the spring rod becomes nearly vertical. So the spring will be assumed to lie in a plane which is nearly perpendicular to the axis of the spring. This axis of the spring perpendicular to the axis of plane. So hence a maintain equilibrium of a segment of the spring, only a shearing force, that is V, is equal to F, and torque T is equal to force multiplied with R are required at any X section, gives torque. So in this analysis of springs, it is customary to assume that the shearing stresses caused by the direct shear force is uniformly distributed and is negligible. The shearing stress caused by the direct shear force, so that is uniformly distributed throughout the spring, so that you can neglect. The shear stress caused due to the torsion, that is twisting moment, that will be considered. So apply torsion formula. Already we have derived in a previous session torsion formula. T by J is equal to tau by R is equal to G theta by L. So using the formula, you have to need to derive the angular twist and then torsion, shear stress and deflections. See, this is a torsion formula which you have derived in the previous session. In this, the T is torque and J is polar moment of inertia, tau is shear stress, R is distance, G is the shear modulus or modulus of rigidity, and theta the angular twist, and L is the length. Now substitute J is equal to pi d to the power of 4 by 32 per circular section, cross section. And T is W into D by 2. So the load is W and with distance D by 2. So you'll get torsion already. Have seen the torque is equal to F into R. So that air force multiply with R. Theta, the deflection, the angular twist, is 2 into X by D. L is equal to pi D into X or 2 pi R X. Now the spring deflection. So by using this formula, theta 2x by d and j is equal to pi d to the power 4 by 32 and torque is equal to w into d by 2. Now substitute here t by j is equal to g theta by L. T by j is equal to g theta by L. So in this equation substitute the torque wd by 2 and j is polar moment of inertia and torque g into theta. Theta is 2x by d. 2x by d and L is equal to pi dn. So thus find out the deflection delta is equal to or x is equal to 8w d cube into n by g to the power of 4. N is here number of coils. The spring stiffness, the stiffness is defined as the load per unit deflection. So deflection of the spring is have derived AW into D cube into N by G d to the power of 4. And now need to calculate the stiffness, the spring stiffness, defined as the load for unit deflection. So the representation is with K and W by X, or K is equal to W by delta, load for deflection. So load is W and the deflection is AW d cube into N by G d to the power of 4. So already we have calculated in this deflection part. So therefore, the spring stiffness can calculate K is equal to G d to the power of 4 by 8 d cube into N. So now shear stress. So WD again substitute. Take T by J is equal to tau by R. So in this substitute, torque and J value, and then tau the shear maximum, and R is D by 2. So calculate shear max is equal to AWD by pi d cube. What is D here? D is the mean coil dia. And small d is wire dia. W load. So that the shear stress is equal to AWD by pi d cube. So these formulas are useful while solving the problems. Next one is Wahl's factor. It's also called as Wahl's stress factor. What is this? So in order to take into account the effect of direct shear, so already I told you in starting slides, the due to the direct load, direct shear stress will be induced. So we are not considering. So why? Because it is a very small value. So this in order to take into account the effect of direct shear stress also, and change in coil curvature, a stress factor is defined, that is known as Wahl's stress factor. So the Wahl's stress factor as K is equal to 4C minus 1 by 4C minus 4 plus 0.615 by C. What is this C? Is a spring index. The spring index is equal to, it is the ratio of mean coil diameter to wire dia. If you are considering this effect of direct shear, how the coil curvature is changed, a stress factor is defined. So you should multiply with this stress factor. So if you take into account the Wahl's stress factor, then the formula of the shear stress, so what is the formula of shear stress? Shear stress is 8WD by pi d cube. AW d cube by pi d cube. AWD. Sorry. AWD by pi d cube. This is shear max. Sorry. This is due to the torsional shear stress. Torsional shear stress. But whenever the direct shear stress, we are calculating direct shear stress. So T is equal to shear stress into 5d cube by 16 for circular shaft. Shear stress multiplied with the pi d cube by 16 into is equal to, it gives torque. So now the shear stress, shear max is equal to 16T by pi d cube. So whenever you are considering Walls factor, so multiply with K. What is K? K is equal to 4C minus 1 by 4C minus 4 plus 0.61, 4C minus 4 plus 0.615 by C. So like this, need to calculate the shear stress. Now coming to the strain energy. The strain energy is defined as the energy which is stored within a material when the work has been done on the material. So whenever the work has been done on the material, there is some energy stored internally. So that energy is called strain energy. So in the case of spring, the strain energy would be due to bending, and the strain energy due to bending is given by the expansion, that is U is equal to T square L by 2E. So what is L? Pi dN. L is equal to pi d to the power of 4 by 64. That is a high moment of inertia. Moment of inertia. So after substitution, we get the final strain energy 32 T square D by E into D to the power of 4 multiplied with N, the number of active coils. So T is the torque, D coil diameter, and D is the small y diameter, and E is the modulus of elasticity. So next, if the closed coiled helical spring subjected to axial torque. Up to now we have seen only axial load, whenever the subjected to axial load. Now subjected to axial torque, T or axial couple. So like this. So in this case, the material of the spring is subjected to pure bending, which tends to reduce radius of the coil. So in the bending, what will happen? The radius of the coil will be reduced. In this case, the bending moment is constant throughout the spring and is equal to the applied axial torque, T. So the stresses, that is maximum bending stress, may thus determined from the bending theory. So that is sigma max is equal to my by I. So bending the stress equation already we have derived. So T into, so here bending stress equation, sigma by Y is equal to E by R. So from this equation, write the maximum bending stress formula, and Y is the distance of the cross section from its neutral axis, and pi I is the moment of inertia, pi into d to the power 4 by 64. So finally we will get 32 T by pi d cube. So this is maximum bending stress. Next, deflection or wind up angle. So under the action of axial torque, the deflection of the spring becomes the wind up angle of the spring, which is the angle through which one end turns relative to the other. This is the wind up angle. So this will be equal to the total change of slope along the wire according to area movement theorem. See how to calculate that wind up angle, we will see in these formulas. Theta is 0 to L integrate MdL by EI, but here bending moment is torsion. So take common T by EI outside and 0 to integrate 0 to L limits dl. Thus T remains constant. So theta is equal to TL by EI. And further simplification, substitute L is equal to pi d n and I is equal to pi d to the power 4 by 60. Therefore, on substitution, the value of theta finally will get 64 T into D n by E d to the power 4. So this is theta. You can write in place of d by d is equal to capital D by small d is equal to C. Spring index. The form of spring index you can simplify. Theta formula. The springs in series. Whenever the springs are connected in series, so how to calculate the total stiffness of the spring? If two springs of different stiffness are joined end on end and carry a common load W, they are said to be connected in series, and that the combined stiffness and deflection are given by the following equation. So W by K is equal to X1 plus X2 is equal to W by K1 plus W by K2. So already here written. Or the 1 by K is equal to 1 by K1 plus 1 by K2. So that is, you can simplify K is equal to K1 K2 K1 K2 by K1 plus K2. So whenever the springs are connected in series. When connected in parallel, the springs are joined in such a way that they have a common deflection X. The deflection is load for stiffness is equal to load for deflection. So then they are said to be connected in parallel. In this case, the load carried is shared between the two springs and the total load is W is equal to W plus W2. So this is common load. This is combination of these two loads. Here stiffness K1 and K2. So deflection is load for the first deflection in this delta Rx is equal to initial load W1 by stiffness is equal to load for deflection is equal to load for stiffness K1. Similarly, in this delta Rx W2 by K2. So now write down this W1 is equal to the total load is W1 plus W2. So finally, we'll get stiffness is equal to, you can write K is equal to K1 plus K2. Whenever the springs are joined in parallel. So like this, you need to calculate the total stiffness of the spring are connected in a series and a parallel. So these are the references I have taken. S. Ramamurtham. The title of the book is Strength of Material. Publishers are Dhanpati Rai Publishing Company and R.K. Bansal. Textbook of Strength of Materials. Publications, Lakshmi Publications and R.S. Kurmi and Gupta. Strength of Material. Title of the book is Strength of Material. S. Chand and Co. Publishers and NPTEL online courses Strength of Materials lecture notes I have taken for this PPT.
Like, share and subscribe. Hit the bell icon for more updates.